So when we met last time, we learned some really cool stuff about how to determine what the shearing forces and bending moments are internally inside of beams. Okay, and to summarize exactly what we did, I made this incredibly busy screen for you to be able to sort of remember exactly what we did. All right, so you might remember that. Well, actually, we could start a little bit sooner and say the problem itself that we solved last time came out of a frame and machine problem. So that really wasn't even what I was thinking about putting on this screen, but you might remember that the upper left free body diagram wasn't even really what we started with. We started with an actual physical scenario of a machine, and then we came up with that diagram. And from there, we found external reactions, right? And so now we have this complete diagram that shows all the forces acting on the beams. From there, we would make cuts in particular segments of the beam where we felt like there wasn't very much changing within that segment. And then based on each of those cuts, we would draw a free body diagram appropriate for each one of those cuts. And from that free body diagram, we would write equilibrium equations. And once we had all the equilibrium equations written, then we could take those and construct these piecewise functions, okay, which essentially collected together each of the little sets of functions that we had for each of the segments, you know, one function for shearing force and another function for bending moment. And with those piecewise functions, we can then plug that into a program or plot it by hand, but we can come up with plots that actually give us what the shearing force is as a function of x, or what the bending moment is as a function of x. One thing I didn't actually spend a whole lot of time talking about last time is why would we care, right? Why is it that we need these shearing force diagrams and bending moment diagrams? Got any thoughts? Okay, so you can calculate these values, the shearing force or the bending moment values at any point. But why would that be important? Oh, okay, so it informs you a little bit about where the failure might occur, and how would it do that? Okay, so we're going to learn a little bit more about this, but there is a factor that goes on here, the bending moment. Turns out that bending moment can be a very important factor with respect to knowing whether or not the beam will fail. And when the bending moment gets higher, if nothing else changes, what we're going to find pretty soon in one of our future lectures is that that's going to lead to an increased amount of stress, and that can be a point where it might fail. And so out of all of this stuff, what do you think might be the critical thing that we would have found out of all of these exercises? Okay, if I was going to say one thing, I would say this point right here. Okay, for this particular problem. Why is that point right there important? It's where your maximum bending moment occurs, right? So if the cross-section of this beam doesn't change anywhere along the length, if it doesn't change, then we could expect that that point that I drew right there might be the location most likely to fail first. Okay, so that's one of the reasons we're doing all of this. But it may have felt, when you were working on all of these steps of this process, it may have felt like that was kind of heavy and cumbersome. Did it feel that way? Like you're having to draw these free body diagrams, do a lot of equilibrium equations, the process of maybe collecting those into the functions or making the plots, that's kind of a lengthy process. Okay, would you like to have a way that makes that a little bit more clean and quick? Okay, well, I have good news for you, because that's what we're going to do today, is learn a way to make this more clean and quick. But we have to do a little bit of theory before we get into showing you exactly how this works. So here's what we're going to do. We're going to develop for ourselves a few rules. And based on these rules, we're going to be able to sketch shearing diagrams, shearing force diagrams, as well as bending moment diagrams, you know, in a much more easy fashion than what we did by working through all those functions. Okay? And here's kind of my starting point that I'm going to ask us to think about. Okay? Think about a beam, and I showed that beam over there on the left, And it just so happens that at a particular point in the beam, we've got all the different possibilities as far as the types of loads that can be applied at that point. Okay, we have a distributed load that happens at that location. We have a concentrated force that happens at that location. We have a concentrated moment that happens at that location, which is also known as a couple. And I'm going to say this as well. I don't care necessarily what's happening elsewhere in this beam. Like there could be other things. I could have another force acting here or another moment here. That's not really what I'm mostly concerned about. What I'm concerned about is focusing in on that little segment that I've identified as between coordinates of XL and XR. And so I've separated out this little chunk of beam, and we're going to look at free body diagrams of that little chunk of the beam. So I've cut that beam out, and because I've cut it out, what do you think happens on the surfaces where I made the cuts? Right? That's what we kind of do before, right? Wherever we make a cut, we have to think about what happens at that cut. So what happens at that cut, at those two cuts? Okay, there could be a shearing force at each of the cuts, as well as a bending moment, a concentrated moment that would be applied at each one of those cuts. So let's go ahead and draw those on here according to our positive sign convention that we learned last time. So on the left end of the beam, what would a positive shear look like on the left end of this little chunk? You remember? Okay, thinking through what would positive sign convention call for as far as the direction that I show the force acting on the left end of this chunk? Okay, pointing up, kind of like this. And let me give that shearing force right there a name. I'm going to call that V sub L for the shearing force on the left end of this little chunk. If I follow sign convention again for the other side, what direction should I show that? Down. And I would call this, I'm going to name it V sub R for the shearing force at the right end of this little chunk of beam. Okay? How about for bending moments? I want to do those according to sign convention as well for bending moments. So on the left end of the beam, what direction should I show the moment so that I'm assuming positive sign convention? Okay, clockwise. Okay, and I'm going to name this one M sub L. And over on the right side, counterclockwise. And I'll name that one M sub R. Okay? So that's kind of the steps of once we've split out this little segment of the beam, thinking about what sorts of forces would act on that little segment of the beam, we've now added those in that we would have to once we've made those cuts. Okay? One other thing, let me define a couple of things. All right? So you might notice there that I defined the difference between XR and XL as delta X. You see that? Which that kind of makes sense, right? It's the difference in our X coordinate going from the left end of this little chunk to the right end of the little chunk. And so we're going to call that delta X. What do you think I might want to call, the difference in the shearing force? Right? If I wanted to define something delta V, how would I define that, you think? Okay, keep in mind, what I'm trying to do is measure all of my X values relative to the left, right? So if I want to define my change in my shear force, you might want to do, actually it might be the other way, right? VR minus VL, right? Because you want to take what it becomes at the end of a movement from left to right minus what it was at the beginning of a movement from left to right. Does that make sense? Okay, so I'm going to define that term delta V as being VR minus VL. And what do you think I might define delta M as? MR minus ML, right? So I'm just trying to have some terms here that we'll be able to use here in just a second. Okay? And what do you do with a free body diagram? Like once you've got your free body diagram, what do you do with it? Like why would you draw one? to solve for forces or moments, right? And you do that with equilibrium equations. So let's actually write an equilibrium equation for translation in the vertical direction, right? We could call that a sum of forces in the y or something like that. Okay? What would we find? Okay? There's a couple of easy ones, right? We've got VL. May as well put VR right there with it too. VL minus VR, right? Okay, I mean, we can do that here in just a second. But let's say it's VL minus VR for right now. Okay? What else do we have acting on this little piece? F. What else? WX. But what do I need to do with WX? Okay? Now you might notice I intentionally made it look curvy. Okay? So some of you have the right idea in terms of saying WX times delta X should be approximately what the total amount of force is right there. But if this thing curves, then actually what this would be the integral from X, what? L to XR of what? WX dx. Okay? And if you care to, you can actually kind of prove this to yourself by thinking of a little slice that is infinitesimally small as far as its width, right? And you could call that dx, right? The height of that little rectangle, right, is going to be w of x, right here at this point, right, where x is now the specific coordinate that I am measuring relative to this specific location where I found that little rectangle. And you look at that, the area under that w of x curve is basically the total amount of force, which is why that, that integral is how we would evaluate the total amount of upward force due to the w of x curve. Okay? Any other forces that would have influences in the vertical direction? Okay? I don't think so. Right? And so what I would say now is maybe what we'll need to do is go ahead and add that definition of delta V into our equation here, and I'm going to pull it out and isolate it. So in other words, if I took VL minus VR and moved it to the other side of the equation, it would negate both of them, right? It would be VR minus VL. Okay? So that would just be delta V. And that's going to be equal to F plus the integral from XL to XR, W of X dx. Okay? And with this little expression right here, we can generate some rules that will make it easier for us to find changes in the shearing function over little segments of the beam. Okay? I'm going to do that in this format. I'm going to do kind of some if-thens. Right? So if, and then over here I'm going to identify the resulting rule. Okay? So my first if is this. What if we have a situation where the concentrated force value is equal to 0 and the distributed load function is equal to 0? We're going to start real easy. Okay? What if those two conditions are met? There's no concentrated force and there's no distributed load function. Okay? What are we going to have as far as our delta V is concerned? It's a really tricky one, right? Okay? There's not going to be any change in the shearing force function. And so this is what gives rise to our first rule. Our first rule is, in a segment of beam where no external concentrated or distributed forces are applied, there will be no change in the V of x curve on the right end relative to the left end. I'll put that right here. Okay? Sweet. Our first rule. Shall we do another one? Yes. We're going to love it. All right? Our next rule is this. What if f is not equal to 0? Okay? And let's also do this. Let's let delta x approach 0. All right? What does it do if delta x approaches 0? Okay? Let me add one little thing on here and say, I'm kind of presuming here, even though I didn't say it, that I've got delta x over 2 and delta x over 2 as far as my widths of this element relative to the middle where these two things are being applied. Okay? So if delta x goes to 0, what kind of an effect is the distributed load function w of x, what kind of an effect does that have if delta x goes to 0? Okay? Well, certainly if f is not equal to 0, then the effect of the w of x function is going to be totally insignificant relative to something that is a finite change that happens there due to f. Well, anyway, if this happens, then what does delta v become? Okay? Basically what happens is you can think of the limits of that integral of wx dx. If those limits, xl and xr, basically become the same point, what happens to the value of that integral? Basically becomes 0, right? So that's why this basically just becomes f, and this leads to our second rule. Okay? Second rule we've got is that an upward concentrated force of F, because notice we showed it upwards on this diagram, and this upward concentrated force of F causes a positive step change of a value of F in the function v of x at the point where it's applied. Okay? That's our next rule. All right, we ready for some more? I thought you might be, so I made some more. All right, the next one I want to look at is what if we do let f equal 0? Okay? And we let this w of x function not be 0, and we let delta x approach 0. So in other words, we're now making the slice of this beam super, super small, right? Which is good. You know, we're making that little slice small. And we're saying f is no longer a factor anymore, but we're going to let delta x go to 0. So let's actually think about what happens with this function. Okay? F goes to 0, so delta v becomes what? Just this integral from xl to xr of wx dx. Okay? Now think of an infinitesimally narrow slice. One infinitesimally narrow slice, right? You're going to have some tiny little change possibly in shearing force, and you're going to have some tiny little change in x location. As a matter of fact, they're so tiny that they're like infinitesimal, right? What does this become? What does this thing become as x goes to 0? Should put this over here, shouldn't I? What does this what happens here? Okay. This becomes dv, right? And what happens with that function and the integral and all that? Okay, the w of x basically can be pulled out like a constant, and you just have dx. Right? And what you see there is that you can solve this and say dv dx is going to be equal to w of x. Okay? So that's what I'm going to put down here in my then spot in this table, right? dv dx is going to be equal to w of x. Okay? So what does that mean in terms of these rules? Here's what I said. The value of the distributed load function w of x at a particular x location is the slope of the shearing force function v of x at that x location. Okay? But you might see there, we did say this is when f equals 0. So what actually happens to this rule when x is not, or when f is not 0? We have a rule for that already, right? If f is not 0, then we have this step change. So there's not even a continuous function at that point, right? So we can't talk about slope so much, right? But everywhere else we can talk about slope. So this is our rule for how the value of the distributed load function relates to the slope of the shearing force function. They're just equal. Not bad, huh? All right, we got another one. We ready for another one? I mean, I knew you were. Okay, the next one I want to look at is what if f is equal to 0 again, and now w of x is not equal to 0 again, but this time we're not going to cause there to be any kind of a narrowing of our x. So we're not making x go to 0. Okay? So now what do we have? Okay? We're going to have delta v being equal to what? First of all, we define delta v as what? So that's actually what I want to do first. What is delta v? Okay. VR minus VL. And what is this going to be? Okay, we're letting f go to 0. This just is that integral from xl to xr of wx dx. Which that's really nice looking calculus stuff right there, but what does it actually mean? Well, I'll tell you what it actually means. Okay, we can say that the area under the distributed load function w of x over a segment of the beam is the change in the shearing force in the shearing force function Vx over that segment. Right? Notice that that's what VR minus VL is. It's how much did the shearing force function V of x change going from one location to another location from left to right. Does that make sense? Take right minus left, it gives you the change that you had from left to right. Okay? And so that's what this gives us. It's the it's going to be the change, the area under the distributed load function over a segment of beam is going to be the change in the shearing force function V of x over that segment. You guys are loving this, aren't you? I promise you, you'll like it a lot better once we get through all this. Okay. I only have one more. All right. The last one I have here is this. Anytime C is equal to 0, or if C is not equal to 0. What I want you to do is look at this equation that we're working off of up here. Delta V is equal to F plus integral from XL to XR WX dx. What's our conclusion if C is equal to 0 or if C is not equal to 0? Who cares? Right? Doesn't matter. C, remember, is the concentrated moment that we could externally apply onto this segment of the beam. Okay? Sorry, I probably should have brought that up again. But C is the concentrated moment that's applied at the center of this little segment. Imagine, like, what this would be is that if you have a beam, if this beam is what we're talking about here, imagine welding on a shaft right there in the middle of the beam, and then a twisting action happens around that shaft, a pure twisting action, right? It's not applying any forces in any direction. All it's doing is applying a pure twisting action onto the beam, okay? And that's what we're talking about with C. So anyway, but our conclusion here is that at least for this equation, whether we have a C or whether we don't have a C, it won't matter, right? And so this is our other rule that I'm going to go ahead and put in here. Okay? Externally applied concentrated moments, right? These are also called couples, by the way, have no local effect on the V of X curve. I said this kind of carefully. What do you think I mean by local effect? Yeah, I've got to be a little careful here because you might notice that if I apply a concentrated moment on my original case, one of the things that it will affect is my reaction forces RA and RB, right? And because RA and RB are affected, it will affect the V of X curve across its entire length because we changed what those, what those two reaction forces were. Does that make sense? So it doesn't have, it has an effect, but it has the effect through the reactions, not because of the locally applied concentrated moment. Okay? So externally applied concentrated moments or couples have no local effect on the V of X curve. In other words, you will not be able to look at the V of X curve where that C is applied and notice any change right there at that point because that C is applied. Okay? And guess what? This is the whole set of rules that we have for our V of X curve. Isn't that exciting? Super exciting. I bet you have no idea what we're going to do next. All right, someone says practice. I tell you what, let's practice in a few seconds because we have something else that I think might be helpful for us to do first. I'm going to shove all this stuff down. Didn't really want to shove this down, so I'm going to try to grab it and move it back up. Okay, all this stuff had to do with our sum of forces in the y direction. What do you think I'm going to do next? Sum of moments. Okay, I'm going to do that right here. I'm going to sum moments around the center. Okay, where this point right here is the center. All right, so what sorts of effects do I have that will have moments, cause moments around the center? And I'm going to suggest, why don't we look at my concentrated moments first. Okay? Like which ones? Okay? Like MR minus ML. And someone says, that would just be delta M, right? That would just be delta M. We'll do that substitution here in just a second. But MR minus ML, then what? Okay? C goes the opposite direction, right? Or it goes the same direction as ML, right? So I would say minus C. Okay? Now what? Does the F have any effect? No. What about VL? And would it have a clockwise effect or a counterclockwise effect? VL would have a clockwise effect, so I'm going to have to count it as being minus VL times what? Delta X over 2. And what about VR? Okay, VR is also going in a clockwise direction around the center, right? So I have to do another minus VR times delta X over 2. All right? Feel good about that? What other effects might I have? My distributed load. I saved the most fun for the last, right? So think about this. My distributed load function there. Okay? How would I figure out what that would do for a moment around the center? Okay? Yeah, what I basically came up with here, this little area of that little rectangle would be something like a dV, right? Or a D, I don't really know. Let's just say dF. A little differential amount of force. Don't confuse that with the variable F that I put on there before. I just need to have an idea that that is a little tiny bit of force, the fact that I've got that little area right there. What effect does that have as far as a moment around the center? Well, it's going to be based on this distance, right? What's that distance? Okay. Well, that center point is going to be XR minus XL over 2, right? Or I should say XR plus XL over 2. So basically, I'm trying to find the coordinate of that center point. The coordinate of that center point is going to be the average of XR and XL, right? So that would be how far it is from the left end to this location, right? It's going to be XR plus XL over 2, right, relative to that left point. So what's that distance? This distance right here is going to be X minus that average XR plus XL over 2. Okay, think of these x's as being coordinates. So the question just now is, can you explain why it's XR plus XL over 2? So I'm going to say, think of each of these locations as x coordinates, right? So if the center, right, is halfway in between XL and XR, another way of saying that is it's just the average of XL and XR. And the formula for average is you just add things up and divide by the number of things, right? So we're adding XL to XR and dividing by 2, and that gives us the x coordinate of the center of this piece. That makes sense? In other words, let's put numbers to it. It might make more sense, right? What if XL was 1 and XR was 2? All right? What should the center be if we knew those two terms? We know intuitively it should be 1.5, right? If the left is 1 and the right is 2, it should be 1.5. Well, think about what would happen there. You would add 1 plus 2 would be 3, and divide by 2, you'd get 1.5, right? So we're just taking the average of the left coordinate and the right coordinate, and it'll get us right to the middle of the segment. Okay? All right. Here's the thing. You might hate me in just a second. I wanted to do this pretty formally so that we could actually write an interesting integral. Okay? The interesting integral I want to write is based on coming up with what I'll call a dm, right? A differential amount of moment. What would this be? Okay, it's going to be that distance of x minus xr plus xl over 2. I'm going to slide this over here a little bit. Okay, so it's based on this distance times df. But what's df? df is w of x dx, right? We came up with that earlier. So how would I come up with my total amount of moment that would be applied by this whole distributed load? Okay. You might notice I'm counting counterclockwise as being positive, which is the same way I'm counting my sum here. So I can add, and someone says use an integral from xl to xr of dm, right? But we'll sub in all this stuff for dm. X minus xr plus xl over 2 times w of x dx. Okay? And that would be my equation for my total amount of moment around the center of this little segment. So now that we've got this equation, just like I did before, actually, I guess one more step here. Let me go ahead and sub in my delta m term, right? So this right here would be delta m. And let me solve for everything. So delta m becomes what? C. Okay. With these two terms right here, my minus VL times delta x over 2 minus VR times delta x over 2, I'm going to change that up a little bit and say, you know, first of all, it moves to the other side of the expression, so they would be plus. But I'm going to factor out the delta x. And instead, I'm going to put in here VL plus VR over 2 delta x. Is that fair enough? So I factored out delta x, and I just left the VL and VR and the factor of 2, or the dividing by 2, all together there. And then what do I do with my integral term? Okay, it was plus over here, right? So I say minus the integral from xl to xr of all this stuff. X minus xr plus xl over 2, all that times w of x dx. Yes, sir.
Could you explain how you determine the sign of the integral?
Okay, so we determined the sign of the integral because the what we call the integrand, right, the thing inside the integral, right? We defined it to be positive, right? The w of x dx is creating a little force. I showed all these little arrows upward. So w of x is positive upward, right? And so this little piece right here would be a net upward force because of that little triangle, and it would be a value of df, right? I took that and I multiplied by this little length, x minus xr plus xl over 2, which is a positive number, right? And that creates a counterclockwise tendency to rotate around the center, which is the direction that I'm counting as being positive in my sum. So I count that integral as being positive when I'm adding them all up. Does that make sense?
I was just, it confuses me because the distributed load on the left side of the center will cause it to turn.
Okay. So his point is that confuses me because what if we were looking at a little element over here? So let's actually think about that. What if we were looking at an element over there? So if we're looking at a little element that's to the left of the center, then what we'll see is that x is going to be less, because this x value is now going to be in here somewhere. That's going to be less than the coordinate defined by xr plus xl over 2. So you'll end up with a negative value in the parentheses, right, times a positive value implied by wx dx, right, which would imply a clockwise tendency to rotate, and you'd be counting it as negative, so that would still be consistent with our counterclockwise positive summation scheme.
So that integral will take care of the entire...
The integral takes care of the entire length because this one term right here keeps the correct sign just based on those coordinates.
The sign will change as we progress.
Right. All right. Now here's the thing. We're going to see in just a second it doesn't matter very much. But I sort of had to put this together to show you that it doesn't matter very much. Okay? So we're going to go to our next phase, and that is we need to write some rules based on knowing this expression for finding the difference in our bending moment over a little segment of the beam. Okay? So we're going to use the same type of format. We'll say if we have some conditions met, what does that mean, right? And then what kind of a rule can we write? Okay. So let's take our first case here to be what if C is not equal 0? Let's do this one first. C is not equal 0 and delta x goes to 0. If C is not equal to 0 and delta x goes to 0, then what is delta m? Okay? Well, you'll notice here, if delta x is going to 0, both the middle term, because it has delta x in it, it's going to 0. It becomes insignificant relative to this C that is a finite value, right? What about the integral that I have over here? Delta x goes to 0, the limits from xl to xr, right, become right next to each other, and we're going to have nothing coming out of that integral. Okay? So delta m just becomes C. And based on that, we can write a particular rule. And here's our next rule. And I wrote this one carefully as well. A clockwise concentrated moment, or couple, which is another word for it, of C causes a positive step change of C in m of x at its point of application. Keep in mind, this is for you thinking of moving from left to right. Your deltas are defined going from to the left toward the right. And you're having a positive change with a clockwise concentrated moment. This is counterintuitive for a lot of folks. I'll explain it a little bit better after a little while, but let's just take this as our rule for right now. The reason we know it's the rule is that I assumed C was clockwise in my original setup, and I worked through the math, and we're seeing here that the delta m is a positive C, right? So we believe it, right? I'll show you more intuitively why after a little while. Okay, so there's our first rule. Shall we write another one too? Yeah, let's do it. Okay, the next rule we're going to do is when C is equal to 0 and delta x goes to 0. Okay. Now what happens here? Okay, so now C goes away, right? This C is gone. This delta x right here is approaching 0, but guess what? Delta m is also probably approaching 0. Okay, what else might be approaching 0? Is all of this approaching 0? Yeah, it's approaching 0, but I'm going to show you something interesting here. There's two reasons that the one on the far right is approaching 0. I already mentioned one of them. When delta x approaches 0, xl is approaching xr, and the integral is going to be 0 just because you have 0 length over which to do the integral. So that's one reason why the integral would become 0. Do you see any other reasons why the integral would become 0? Look at this term right here. If delta x is going to 0, then the term that is the average between xr and xl is approaching just x. Like there is no other place for x to be besides right there at xl plus xr over 2. And so we see here, not only are the limits of the integral approaching 0, but also that term right there is approaching 0. And it would be really kind of onerous for me to go through and really formally mathematically prove it. But you guys might remember when you were in math class, you studied some, I think you might have called it L'Hopital's rule. Okay? What did that basically do when you thought of L'Hopital's rule? Okay. Yeah, so I think part of it was you had the higher order terms. When you had a higher order term that was where that term was approaching 0, did those terms matter relative to the lower order terms? No. So what pops out of this, if I was to actually do all that very formally, what pops out of it is that far right term actually ends up with a higher order of your delta x because of how that is defined. And it becomes to where that far right term ends up being basically insignificant as x goes to 0 relative to the middle term, right? This term right here is more significant than the one that's in the red parentheses there because it's a lower order term. And like I said, I'm not going to go through and prove that real formally, but that's what's going on with this. And so what can we conclude as delta x goes to 0? Okay. Well, we can say delta m, tell you what, let me solve it out for delta m over delta x. This is going to be equal to VL plus VR over 2. But keep in mind, we're taking this limit, right, as x goes to 0. So what happens to this? The delta m over delta x becomes dm dx. And if we're taking the limit as x goes to 0, what is VL plus VR over 2? What's another way we might be able to say that? To be fair enough maybe to say that's just whatever your v value is at your coordinate of x. Right? Keep in mind, if you let these two limits come inward, right? The limit here come inward and the limit here come inward, you're going to focus in right there on the center, and at some point when delta x goes to 0, that's just whatever the shearing value is at that location in the beam. Okay? And so this is what we end up with. Okay? And so what kind of a rule can we generate out of that? Okay, we will say here the value of the shearing force function at a particular x location is the slope of the bending moment function at that x location. Okay? Okay, shall we do another one? Yeah, we're on a roll, right? What if we just let C equal 0? Okay? And this one may be a little bit confusing, but when we let C equal 0, we can think of how the how this bending moment is changing over the length of this little segment based on how the slope of the mx function relates to the vx function, right? In other words, I've now determined that dm is equal to vx, or v of x, dx. Could I think about integrating this, right, from xl to xr? And I integrate this from ml to mr. What do I get on the left side? mr minus ml, which is just delta m, and it's just going to be equal to the integral from xl to xr of v of x dx. Okay, so this is how I'm going to write that over here. Delta m, which is defined as mr minus ml, this is just going to be equal to the integral from xl to xr of v of x dx. All right, so what kind of a rule can I write from that? This one right here. The area under the shearing force function v of x over a segment of beam is the change in the bending moment function m of x over that same segment. You might notice that mr minus ml would be the change in my m of x function going from xl to xr. Make sense? So the area under that shearing force function v of x basically gives us the change in m of x. Okay? We only have one more rule, and then we get to do an example. We ready for our last rule? Okay. F equals 0 or F doesn't equal 0. Who cares? Okay. What do we mean by this? Basically, this is our last little rule we're going to have here. Okay. An externally applied concentrated force does not cause an immediate local change in the value of the bending moment carried in the beam. I worded that carefully as well, right? Does it cause a change in the bending moment of the beam? Yes, it does, because it causes a change in the v of x function, right? And the v of x function in turn has an effect on the bending moment function. But we won't see anything in particular on the m of x curve in order to notice that there was a force being applied. About the best we can come up with is it probably will cause an immediate change in slope of the m function. That's something that we can maybe expect. But you know, we're not going to expect there to be like an immediate change in the value of the m of x function. Great. You guys have really hung in there with me. This is a lot of stuff, but I wanted you to see the justification for all these different rules. And now what I want to do is show you an example where we use all these different rules. Is that acceptable? I hope so. That's where we're heading. So we're going to do this example right here. Our instructions are draw V&M diagrams, right? That stands for shear and bending moment diagrams, for this beam, and find the maximum bending moment that the beam experiences. Okay? I'll give you, one guess. What do you think our first step is for a problem like this?
Free body diagram.
Okay? A free body diagram is a good idea. How do I make this a free body diagram? Okay? Free the body. It means the roller at G I need to replace with what? The reaction that it would carry, right? So that would be maybe RG would be a good thing to name that. What about at A? Okay? We could, since it's a pin at A, it could have both components of reaction. But will it? It won't, because there aren't any externally applied forces that have X components or horizontal components, right? So I can just go ahead and put that in as just a vertical just to make it less confusing. And I'll call that RA. How do I find RG and RA? We can sum moments, maybe about point A, right? What I'll have there is minus 900 pounds times 4 feet. Okay. What do I do with my 120 pounds per foot? Okay. Basically what we're doing is we're going to concentrate it all at the middle of that segment where it's applied, and it's going to have what value? 120 pounds per foot times 12 feet. Okay. So I'll just leave that alone, and we'll just put it in our sum. I'll deal with it all at the same time. So what effect does that have? Well, it'll be minus 120 pounds per foot times 12 feet times what? Okay, 10 feet plus, okay, what I'm trying to do here is I need to figure out the distance of this line of action away from point A. So it'll be 10 feet plus 6 feet, right? So 16 feet. Okay, what else in my sum? Plus 2,000 foot-pounds, right? Taking counterclockwise to be positive, that's a counterclockwise concentrated moment there, so I just add it into the sum. And then I add RG times what would that length be? Okay, 10 plus 12 would be 22, plus 4 would be 26, plus 6 would be 32 feet. Okay, and in the interest of time, I tell you what, I'll just tell you how this comes out. RG calculates to be 770 pounds. Okay, how do I find RA? Some forces in the y direction, I'll have RA minus 900 pounds minus 120 pounds per foot times 12 feet. Okay. Do I do anything with my 2,000 foot-pounds? Not for my sum of forces, right? It doesn't show up there. But I do take into account RG, so I add 770. Okay, and based on this, RA winds up being 1,570 pounds. Okay. I wanted to do that relatively quickly because that's not my main thrust of this problem, right? We have other things we got to get to. So RG, let me put it in here as 770 pounds. And RA, let me put it in here as 1,570 pounds. Good? All right. I'm going to get rid of this. All right. Now what we're going to try to do is just immediately draw the shearing force and bending moment diagrams basically with those rules that we identified just a few minutes ago and not really much else. Okay? So what I'm going to do here, you may actually have noticed, I'm going to try to draw this to scale. So you might have noticed that I kind of carefully counted my squares when I drew this diagram. Each square is a foot left to right on my graph paper. Okay? So I'm going to do a pretty good job here of trying to draw this thing to scale. Okay? And I'm going to show the, my 0 axis for my V diagram. I'm going to show it right here. And I'm going to need more room for my M diagram than my V diagram. So let's say this is V. And I'll say this is in pounds. Okay? And let's actually think about this first. To the left of A, how much shearing force will it carry? 0. Which is a good thing, because our beam ends there, right? We got no material to the left. It better not be carrying force. Okay? So there's no force to the left of A. So we can actually start by saying, if I was thinking about going to the left here, I better be starting at 0. And now I'm going to identify changes as I move from left to right of things that happen in my V diagram. And let's go back to our rules and see if we have a rule for the very first place that there might be a change. Right? Where might that be? At point A, right? There's something that happens at point A. And what do our rules say should happen in my V diagram because of that? Which of these rules would be applicable here? Okay. F is not equal to 0 and delta x goes to 0, meaning right there at this point where this force is being applied, I'm going to have a step change of F, right? An upward concentrated force of F causes a positive step change of F in V of x at its point of application. What does that mean on this diagram? I'll tell you what. I'm going to go up by about 3 squares. What am I saying a square is? A square here is about 500 pounds or so. Okay? Because I'm going to go with an upward step change of the value of my applied force, 1,570 pounds applied at A. It's a concentrated force applied at A. Okay? Now what happens between A and B? Okay? We have a rule for that, believe it or not. Right? In a segment of beam where no external concentrated or distributed forces are applied, there will be no change in the V of x curve on the right end relative to the left end. So that means we can draw a straight line to where the 900 pounds is being applied. Now what happens where the 900 pounds is being applied? Our rule that we just used a second ago for the 1,570 pounds applies again, but this time the force goes down, not up. Right? What do you think that does to our shear diagram? It's going to go down about 2 squares, right? Now, let me actually write these in here so we don't lose them. This value right here was 1570. We're going to go down to what? Okay. Well, here's where we actually do need to do a quick calculation, because this value right here was the 900. 900 pounds. Okay? And so we need to take 1570 and subtract 900. That gives us 670, right? And that applies till we hit the beginning of that distributed load. Again, based on rule number 1. All right. Now what happens here? Okay. The first thing I want to make a huge emphasis on is once you get to this point, right, you used that lumping of that distributed load to find external reactions, right? You are not going to be using it to find these V&M functions, right? So I'm actually going to go ahead and erase this sucker up here because it doesn't matter anymore. We found the external reactions. We don't need that anymore. We need to look at the actual applied load, the actual nature of how it's applied. Okay? And it is this constant downward distributed load. Let's see what we have as far as rules for that. Okay? My distributed load here is not equal to 0. It says here, the value of the distributed load function at a particular x location is the slope of the shearing force function at that x location. Well, my value of my w of x function stays the same across this whole segment, right? What does that mean for the slope of my v function? Stays the same, which means it's a straight line. Okay? So I can tell by that rule that whatever happens from point C to point D should be a straight line. Okay? It won't be a flat straight line anymore like horizontal, right? But it'll be a straight line that now is going to have some slope to it. The slope value it has is going to be negative 120 pounds per foot of length. Okay? And that makes it really make sense, this other rule here that says the area under the distributed load function over a segment of beam is the change in the shearing force function v of x over that segment. Okay? So what's the area of the distributed load function? 120 pounds per foot times 12 feet, right? Let's actually go ahead and figure out what that is. 120 times 12, okay? It'll be a change of 1,440 pounds over that 12 foot of length, which means that what I can do here is, I'll take my 670 and subtract the 1440, right? So 670 minus 1440 will give me negative 770. And what happens here is that that's going to go out to where this end of this thing is. And what was that? Negative 770? Okay. So I can say these are 500 each, right? So maybe it'll be somewhere in here. All right. And to make it super clean, I use my little line tool. All right. Now, some of you might think, man, I wonder if that concentrated moment right there would have any effect. Because we know that between D and E, there won't be any effect. That was rule number 1, right? Between there, it's not going to have any effect on that curve. So that's just going to stay at this negative 770. And just to be clear on this, let me also do this. Let me say, just to really identify it, that between here and here, this was a change of 1440 pounds. Okay. So now we get up to that concentrated moment. Does it have any effect? All right. Go up to our rules. externally applied concentrated moments or couples have no local effect on the V of x curve. So we just burn right through that place where we otherwise would have maybe been confused and thought there should have been some sort of a change. We understand that there will not be. We just keep on rolling till we get to this other applied force of 770 pounds. We're at negative 770. An upward concentrated force causes a positive change, which takes us up to 0, which makes us very happy. Why is that? It better be 0, because we don't have any more material to carry anything that's not 0, right? We made a mistake somewhere along the way if we get to the end and it's not 0. Okay? Wonderful. This is our shearing force diagram. And the shearing force diagram means a little bit to us by itself, but not that much. What matters to us more about the shearing force diagram is its ability to help us find things with respect to our bending moment diagram. Because the bending moment is actually the thing that is a little bit more of a factor with respect to whether or not our materials will fail due to bending. Okay? So we need to go on and do our next, this next one. And I'm going to go ahead and down here, let me say, I'll make this my 0 point, right? This is for my X location. I'm going to say I'm about to plot M, and M is going to be in foot-pounds. Okay, I'm going to start with the same question. To the left of A, how much bending moment is my beam carrying? 0, which is good. It better not be carrying anything because there's nothing there to carry it. Okay, so I'm starting at 0. Now let's think about what we need to do next. Okay, so there's going to be some kind of a change that happens because of the concentrated force RA, but not something that directly happens because of that concentrated force RA. We need to go up and look at our rules for bending moment. Okay? What is it that causes the bending moment function to start changing? Okay? Notice here we have a non-zero V of x value starting at point A. Right? We now have a non-zero value of my V of x function. So what does that do to some of our assumptions or some of our rules that we have for our bending moments? Okay, first of all, the value of the shearing force function at a particular x location is the slope of the bending moment function at that x location. So what does that mean our shape of our curve should look like between A and B? Should be a straight line, right? Because we have a constant value of the V function. So we should have a straight line starting here and going to wherever this next transition happens. Okay? And how much change is there going to be? Well, let's go back up and look at our rules. The area under the shearing force function V of x over a segment of beam is the change in the bending moment function M of x over that segment. So that means that with our slopey line, it's going to be a straight line, but with a slope going from this point to somewhere along here, right? Our total change is going to be equal to the area right here. Okay, 1,570, okay, that's going to be in pounds, right? Times 4 feet. Okay, so 1,570 times 4 feet gives us 6,280, right? And I tell you what, let's make each of these little squares 1,000. Okay, so 1, 2, 3, 4, 5, 6, and then, somewhere in here, right? So I'm going to put that point right there and say that from one point to the other is going to be a straight line. The difference in height that we'll have right there is going to be that 6,280, was it? Okay, which means that the value right here is 6,280. Right? That's what that point right there, the value of that point is 6,280 foot-pounds. All right. Now what happens on this curve? Can we use that same rule again, right? The area under the v of x curve is equal to the change in the m curve over a particular interval. So I can go in here and say, what if I found the area in this segment? What would that give me? Well, the value it gives me is 670 times what? 6 feet? All right. That'll be a change of 4,020. Okay. Which I'm going to note that, 4,020. Whoops. Not 420, 4,020. So I'm going to write that down right here. How come I use what? Okay. What we're trying to do is find the area under the v of x curve. The question was, why do I use 670 instead of 900? 900 gave me the change from what the shearing force was on the left side of point B, right, to what it was on the right side of point B. The change is 900. But that means the new value of the shearing force between B and C is going to be 1570 minus 900, right? So it gives me 670 as the value of my v of x curve in segment BC, right? And now what I'm doing is I'm finding the area under my v of x curve to find my change in my m of x curve, okay? And that change is going to be 4020, and I'm going to add that to 6280, which gives me 10,300, okay? Let me count some squares here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a little bit. So this would be my next little curve. Okay. I'll tell you what, I'm going to move this over a little bit, put it right here, and indicate that the change in height right there is that 4,020, and it makes it to where this new value that I just came up with at this location is that 10,300. Okay. Now our first little tricky thing. What we have now is a slopey v of x curve. Okay, and keep in mind, one of our rules up here was that the value of the v of x curve is the slope of the m of x curve at any given point. Okay, so that means that I start off with a positive slope that'll have the same slope value coming out of here, right? It's going to keep the same slope value initially because it has the same height right here at this point on the v of x curve. But then it starts to slope gradually as soon as it starts coming away from that point. It starts to change As a matter of fact, it gets to where it has 0 slope on the m of x curve, right there where the v of x curve crosses the 0 point on this axis. Okay? How do I figure out what that point is right there? Okay? Keep in mind, slope is equal to rise over run. Okay? We know the rise. I'll say rise over run. We know that for this little triangle right here, we know the rise is 670 pounds. We want to know the run. We also know the slope is what? We don't care about the sign for particularly at this point. The slope is going to be 120 pounds per foot, because remember, the value of the w of x curve is the slope of the v of x curve. So what is that little run? It's just going to be equal to 670 pounds divided by 120 pounds per foot, right? Does that make sense? So 670 divided by 120. Whoops. 5.58333. So that would be this little length right here. .5833 feet. And that point matters to us, right? Why does that point matter to us? That's going to be where our peak happens, right? Somewhere up here. Well, how do I figure out how high that peak is? Okay. I need to know the little area of this triangle right here. So use a different color even. Say, what's the area of that triangle? So what is the area of that triangle? Okay. 1/2 base times height, so 0.5 times the base, which is 5.5833, times the height, which is 670. Right? That gives me 1,870.4. How do I use that? That's going to be the difference, right, that happens right here. 1,870.4. Right? And we're saying this is sloping up, but it's getting closer and closer to having 0 slope, right? I'm going to take that 1,870.4 and add it to 1,000, or 10,300, I should say. Okay? 12,170.4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, somewhere in here. Right? This curve goes up and has 0 slope once it gets to that point. And that value is 12,170.4. Okay? Well, now what? All right. Yeah, we probably want to figure out, what is the, let's see, what is the area of this next little triangle right here? Okay? So what we need to do there is we need to take 1/2 times the base. What's the base? It's going to be equal to 12 feet minus 5.58333, right? That makes sense? We need now this other part, this length over here. Okay? So that's what I did there, is 12 minus 5.583333, okay, times the height. What's the height? 770, right? And this will all be actually negative, right, because we're going to be sloping back down from here. So I take all of that and subtract it from 12,170.4. Which gives me 9,699.9. We'll just say 9,700. Okay, so let me count that up from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10. So this keeps on curving down like this, right? And this value that we reach at this point, I just said was 9,700 or so. Okay? And that's because of a change here between this location and this location of how much? All right, 2,470.4. I'm trying to document like every little piece, right? I'm trying to show you we had this change that we added on to what we had before, right? It gets us down to a new location. Then what? How much change now happens here? Okay. 770 times 4 feet, right? 770 times 4. 3,080. Okay. So the change there is going to be 3,080. Let me write that on here somewhere. We haven't got there yet, right? We're coming up to that pretty soon, right? We're doing this little segment from D to E right now. So I need to take that 3,080 and subtract it from 9,700. Which takes me down to 6,620. 1, 2, 3, 4, 5, 6.5 maybe or so, somewhere in there. This will be a straight line in that segment. The difference there is that 3080. Okay. And the value right here at this point is that 6620. Okay. So someone just asked the question, what about that concentrated moment? Okay. Well, let's go up and look at our rules. A clockwise concentrated moment of C causes a positive step change of C, right, of that value of C, in M of X at its point of application. Okay? What direction is ours? Counterclockwise. So I don't have a positive step change, I have a negative step change. Okay? So I drop this by 2,000 foot-pounds. Straight down, right immediately right there. So that gives me what at this location? Okay, 4620. Okay. And then my last little segment is going to be, let me get this last different little color here, maybe pink. I already got that. Let's see. I don't really care. Let's say gray. Okay. What's the area of that segment? Okay. Okay. It will drop by 770 times 6. Takes me down 4620, which is good, right? So I have to get down to 0. Okay? Now, one last thing to touch on. I know, let's give me just like 1 minute here. I'll show you something. This causes a lot of people grief to think that a clockwise moment causes a positive step change on these diagrams, and a counterclockwise moment causes a negative step change. Right? Because everyone's like, counterclockwise, it's always positive, right? Every time we do anything, it's always positive. Let me show you why this is the case. Okay? Think of a beam where the only load applied to the beam is a clockwise concentrated moment. If that's the only force applied to the beam, then what would keep it from spinning? Well, let's say it's got reactions at the two ends. So if it had that, what would the direction of those reactions be? Something like this, right? And what shape would that beam take on? Like, think about how would it end up deforming? Okay? It'd do something like this, right? What kind of a bending moment do you have to the left? This is frowny, right? What's frowny? This is a negative bending moment. Over here, it's smiley. It's got a positive bending moment. What's the effect of that concentrated moment in a clockwise direction? Must have been a positive step change because it went from being frowny to being smiley. Right? So it does make sense that a clockwise concentrated moment causes a positive step change going from left to right. Okay? So that's, this has helped a lot of people to think about it, just illustrating it like that. Okay? I know we're out of time, so I will see you guys next time.